Hi, this is Mrs. Often, and today we're going to talk about modeling using exponents and logarithms. So we've done a lot of work in past math classes with fitting a line to data, the line of best fit, with looking at models that were polynomial functions, but oftentimes data does not fit to a linear model or to another polynomial function. When this happens, there are a number of exponential and logarithmic models that can help model that data. So we're going to look at 5 of them. The first one is exponential growth. Okay, exponential growth we're very familiar with. Looks like this. I've made mine with base e. So the equation for this graph is y equals a times e to the bx power. This is used for compound interest, and it can also be used for population growth. I would say the best use of this for population growth is in the movie Gremlins. Remember, don't feed them after midnight, and definitely don't throw them into a bucket of water. Our next example is exponential decay. Exponential decay is exponential growth reflected in the y-axis. The equation for this looks very, very similar, except that I have a negative exponent. You can also achieve this by having a positive exponent, but having a value for the base that is between 0 and 1. Okay, so that is what is most frequently used for radioactive decay or half-life problems. It's also used for carbon dating. Now, I put carbon dating separately. It is really a special case of radioactive decay. It's used to date very old things. So exponential decay. Also, I guess we could use this in terms of how valuable is your new car after a certain amount of time. So we could try and map that to an exponential decay function. Okay. So the Gaussian distribution is better known as the normal distribution or the bell curve. So here's my bell, ding dong. And this is beloved by statistics teachers. And it was even beloved by many of my college professors who would try to distribute the grades along a bell curve. I had one professor who tried to do this in a class with 5 students, which is statistically a very bad idea. So the equation for this is kind of complicated looking. It is y equals a times e to the negative x minus b squared divided by c. Now you may say, hey, this looks kind of like that exponential decay formula. You know, it has a negative exponent. The difference here is that that negative exponent has a squared portion to it, and that's what causes this nice symmetry. Okay, this is a beautifully symmetric curve. It's used all the time for standardized tests. SAT, MCAS, ACT, IQ tests, they all use this Gaussian distribution, and it's a critical part of statistics. So when you hear the bell curve, now you know what it looks like. Okay, logistic growth is another commonly used model. It's also called a sigmoidal curve. The equation for logistic growth is y equals a over 1 plus b times e to the negative rx power. Now I think it's really funny that this is rx here, because one of the most commonly used models, or most common uses for this model, is the spread of disease. See, first not too many people get sick, then everybody gets sick, but then everybody who can get sick has gotten sick, so it kind of flattens off here. Learning is another use for this model. You know, if you start a new task, maybe you're really, really bad at it, and then you get a lot better, but then your skills kind of flatten out. Maybe you've seen this in things like weight training. And also there are some populations that grow first very quickly, and then they flatten out. So sometimes like bacteria cultures or animal populations will grow according to this logistic growth model. You see, here's my little people sneezing and being grossed out by it. And finally, we have a logarithmic model. The logarithmic model looks like this. We have equations listed here for common log and for natural log. Y equals a plus b times log of x, or y equals a plus b natural log of x. The two most common uses for this logarithmic model is earthquakes on the Richter scale, and that's why you hear these very low numbers for earthquakes that are so damaging. You know, you may think, boy, the earthquake here was only a 2 on the Richter scale, but one that was a 4 knocked down that building, and one that's an 8 is like Armageddon. So that's a logarithmic scale. Sound levels, decibels, are also measured using a logarithmic scale. So it is another very popularly used model for modeling data. And these are the 5 most common models that you will see that utilize exponential and logarithmic information.